Hello, this is LameGuy64 of Made to Tech Productions, and sorry for the lack of content yet again because school and personal life crap got in the way for me. However, I was able to put together something really interesting that's PlayStation Homebrew related and is an impressive programming feat to achieve, which I'll be showing to you in a moment. I worked on it while I was away from work, making and uploading videos, and that routine that thing I was working on is a custom 3D model rendering routine I made entirely in assembly language, and I also developed a custom file format for handling 3D models to be used with the said routine. I've developed it with the help of my DTLH 2000 equipped PC, and also a bunch of documentation found in the PSXDev website and forums. And well, let's get to it, shall we? So this is the test program I made to test my model rendering routine, which is written entirely in MIPS assembly. And it's running on my SCPH700 model PlayStation, recorded via S-Video at 60 frames per second, because why not? And as you can see, it's rendering this 3D model of a manta ray girl, which I modeled myself as a fan art of one of Blargan69's characters from his astronautical series, the manta ray girls. And if I remember correctly, this model is composed of, I think, 291 vertices and 450 triangle strips, including textured and non-textured triangles. I didn't bother to add support for quads in my routine and SMD model file format because quads are somewhat annoying to deal with in Blender, because they can, when you export them, they tend to come out as incorrect and you get weird problems like that. And also the GTE does not support performing rotation, translation, and perspective transformation of four vertices at once. It can only handle 3. So, and I want to focus on speed over supporting something that I typically do not use, like quads. So yeah, and also besides, the quads are still like affine triangles. But anyway, this is the standard rendering routine I made. I wrote, which features your typical Gurod shaded lighting that you've seen in many 3D PS1 games. The PlayStation can actually handle 3 light sources at once, but it does not support specular lighting, and it doesn't support I don't know what it's called, but it's basically if the light source is far away from an object, the object doesn't get influenced much by the light source because the light source is far away. It doesn't support that, so you'll have to perform those calculations in software instead. So not only did I make a Gurod shaded rendering routine for rendering models, I've also written of my custom format. I've also written a cel-shaded version of it. It's more or less the same as my old rendering routine that I've shown off several months ago in an old video where I demonstrated successful cel-shading effect on the PS1. The algorithm is more or less the same, except this one uses bit shifts to divide the vertex colors rather than vertex color values rather than divide, because bit shifts are faster than divide. And also this one is written entirely in assembly, while the old one was written mostly in C with some inline assembly routines, mostly to just communicate with the GTE. And I've also made a environment map version of the rendering routine, which makes models look like chrome, which is pretty freaking cool looking out for the on the PS1. You can see here, it really looks like it's like chrome, sort of similar to the effect you'd see on Mario 64 when Mario becomes Metal Mario, and the Rareware logo in GoldenEye, more or less. The only difference is that they use different environment maps or reflection or chrome maps. But anyway, the routine is a bit glitchy, as you can see here. Mostly comes down to the black seams of the environment map I'm using in this test program, which can be solved by removing those black seams around the circular environment map by enlarging it. But anyway, let's go back to the cel shading because it looks cool, and I'm going to show other 3D models that I've included in the test program. So this one is an old 3D model I made of Nerdsman567's Marilyn character. Well, it looks like crap compared to this. This one's really old, and I could do better than this nowadays. There's a standard smooth cube or rounded cube, a Gouraud shaded rounded cube, and we got sphere, where this is where the cel shading really shines, and then this environment map. And the reason why the environment maps here look super bright is because of the way how the PlayStation handles vertex colors. When you're drawing textured polygons, it takes vertex colors as 128 is neutral, 255 is 50%, 50 I think it was, or 50% brighten, and then any value below it will be dark, will be 0% brightness basically. And we got the logo of Lumdrop's logo in 3D. This one is a smooth shaded version, which allows chrome map and cel shading to look cool on it, but not Gouraud shading. And then here's a hard-edged version of the model. It looks good in smooth shading, but not in cel shading. Not very impressive here. And I got this diamond model. It's supposed to make I made this model to test the environment map while I was testing environment mapping. It's supposed to be sort of like a shiny gem thing, but it didn't turn out the way I wanted it to look, and the vertex colors are a bit too bright for the environment map to look correct. And a normal 3D cube. So, well, that's pretty much it for this test routine. Let's go back to my manta ray model because it's the most interesting one we have here. Oh, and I also made my own version of the per-vertex animation routines, which I'm going to demonstrate now, which allows me to, well, interpolate 3 models between keyframes for, well, animation. Unlike the MIME routines that came with the PsyQ SDK libraries, this one is more efficient and optimized than the routines Sony made, because my routine only contains the keyframe data or the vertex differential data only contains vertices that have moved. It does not contain vertices that haven't moved, whereas the routines provided by Sony will contain pretty much all the vertices at once, which is pretty wasteful. Performing interpolation on vertices that haven't moved. Also, interesting thing about having an animation mechanism like this is that you could like mix multiple keyframes together to, like, for example, you want to make the head move independently from the body. You could just have keyframe information for the head movement, and then have keyframe information for the body movement separately, and you could interpolate them individually to perform individual keyframe animations you want. I don't know, it's pretty complicated to explain, but when you're doing per-vertex animation on this thing, on the PS1, you'll get the idea. It's basically mixing different positions together. So yeah, that's pretty much it for this test program. So let's head off to the source code, the assembly code, explaining briefly how it works. I'm not gonna go full in depth to it, otherwise this video would take forever. But anyway, let's jump to screen capture and see what the assembly code looks like. So here's the source code of my model rendering routine, written entirely in MIPS assembly. And as you can see, if you're not a programmer, let alone one that knows assembly, this makes absolutely no sense whatsoever. And well, actually, if you go into assembly, it's not very difficult once you get the hang of the instructions and how to perform arithmetic efficiently. But it's just slow to work with because you're writing your program instruction by instruction, and performing complex arithmetic would require several instructions to perform said arithmetic. And yeah, I'm not really worried about showing off source code because it'll be open sourced sometime soon in the future anyway. So this is just to explain how some of the innards of how the PlayStation does things like 3D graphics. So in this case, I'm gonna talk about how the PlayStation PlayStation program communicates with the GTE of the PlayStation, or the geometry transformation engine, which is responsible for doing the 3D calculations needed to achieve 3D graphics on the PS1. And what's interesting about MIPS architecture is that the coprocessor instructions are somewhat generic. You have instructions for loading values to the control and data registers, and then you have COP2 to perform an operation with the coprocessor. This allows the architecture to support pretty much any kind of coprocessor, whether a floating point unit or a dedicated geometry engine, in this case of the PlayStation 1. And even in Nintendo 64 probably has a similar mechanism, use of these coprocessor instructions when talking with the RCP, or reality coprocessor, which helps with 3D calculations on N64 games. And well, in the PlayStation, the GT is actually integrated into the CPU as a CPU die as a coprocessor, along with the MDEC processor, which is responsible for decoding FMV video from the disk and such. So here in the LWC2 instructions, what these do is that they will load a value from memory, in this case from registers T1, T2, and T3, which are loaded to contain memory address to vertex vector coordinates. In this case, we're loading 3 vectors at once. So to the GTE, these registers translate to XYZ0, XYZ1, and XYZ2. The GTE can perform rotate, translation, and perspective transformation of 3 vertices at once, and this is why I only support triangles in my rendering routine, because the GTE can perform this. And if you want to do quads, you have to perform calculations of 4 vertices at once, and you have to do the calculations individually rather than at once, and is somewhat less efficient. Also, when you modify either the GTE control registers or data registers, you have to perform at least 2 instructions that don't interact with the coprocessor instructions. You can either use NOP instructions or perform some arithmetic before you perform the coprocessor operation. In this case, it's rotate, translate, and perspective transformation of 3 vertices at once. With this, what this does is that it'll rotate and translate the vectors loaded here, and then it'll perform perspective transformation to convert the 3D coordinates into 2D coordinates so it can be rendered on the screen.
because the PlayStation's GPU can actually only draw to the polygons. It doesn't take any Z value whatsoever. That's why you see problems like clipping and texture distortion. Unlike the N64, where it has things like proper Z buffer, perspective correct texture mapping, and stuff like, and even anti-aliasing. Then you got instructions for reading values from the controller data registers like CFC2. That's from the control register. This one is data moved from coprocessor. It takes a value from the coprocessor. Here's the logic for testing if a triangle is outside the screen bounds, and if the triangle is outside the screen, it'll be discarded. And then here's the logic where the clip testing is done. And then here's where the Z depth value is calculated using the AVS-Z coprocessor opcode. And then here's where lighting is done for logic for flat shaded polygons, Gouraud shaded triangles, texture map, flat texture map triangles, and Gouraud texture map triangles. And then move further down, we have the logic for generating the primitives that draw the polygons that were calculated a while up there. And yeah, that's, I guess, pretty much it for this routine. I'm not gonna go very in depth to this because it will otherwise take forever. So anywho, I'm not sure if this will work in PSX SDK with its assembler, but because this routine is written specifically for the PsyQ SDK assembler. But if it does compile with little or no modifications whatsoever, it should in theory work, as long as you got the GTE properly configured and you have a properly cleared ordering table for this routine to sort primitives to. So yeah, that's pretty much it for this part, and well, yeah.
So there you have it. Even though I don't upload videos very often, I am at least working on something very interesting when it comes to PlayStation Homebrew at least. So if you're subscribed to me or are planning to, remember, when I'm not uploading videos, it's most certainly because I'm working on something or I'm busy with personal stuff. And also, this rendering routine that I made is actually part of a sort of an experimental game engine project that's designed specifically for the PlayStation. It's codenamed Project Scarlet, and it's basically going to be my first venture into 3D game development on the PlayStation, no less, a console that cannot do floating point calculations at all, or it can, but it's very slow. So yeah, you have to use fixed point mathematics, which I know how to do. So anyway, like, comment, subscribe if you want, and LameGuy64 is signing out, and catch you later next time. What? No. Catch you, I should point out that even though my current Detail H2000 PC is still working well, it has sort of developed a problem where if I start up the computer from a cold boot, it would take a very long time to start up for some reason, where there will be no display, the hard disk doesn't spin up, CPU fan doesn't spin, and the CD-ROM drive doesn't initialize for some as if the motherboard is not turned on or something. But after about a minute roughly, it will picture again and start like normal. I don't know what's the cause of it. I'm not sure if it's because of the processor upgrade. When I upgraded the processor from a Pentium 3 450 to a 550 megahertz Pentium 3, which I think took more volts, might be due to that. However, even though if I could fix the problem by downgrading the CPU to the old 450 megahertz, I'm planning to move the DTLH 2000 boards into this thing, the Dell Optiplex GX110. This has a Pentium 3 930 megahertz processor, same amount of RAM as that, but this one can support 4 gig hard drives, and it has a really nice card cage assembly where the expansion cards go to. Well, currently I cannot install the DTLH2000 boards on this because this one currently doesn't have ISA slots. So what I'm doing is that I'm currently waiting for my ISA riser riser board for this to replace the default PCI only riser board that goes to the card cage with one that has 4 ISA slots. So I plan to move the boards from this into this one, which I think would be a better home for the boards because it has a proper card cage with a proper holder for extra long cards. And I'll be trying to see if I could get the DTLH2000 working on this with Windows 2000 using the supplied NT drivers. And if I can't get the DTLH2000 to work on 2000, I'll have to do it, reformat the whole thing into Windows 98, which I don't really like exactly. I don't mind 98, I just don't like its stability issues. And if I ever start doing the board transfer and installation, I'll try to document it to show how annoying possibly it would be to install a DTLH2000, manually installing drivers, stuff like that. But anyway, LameGuy64 signing out, and catch you next time.